The next speaker is Elchanan Mossel from MIT. The title of his talk, Variations of Hyper-Contraction. And please don't leave after Arthur wants to make an announcement.
So thank you very much, Arthur, for the invitation to speak at this conference and to attend this conference. Let me say that it definitely takes me out of my comfort zone, and I hope I'm not going to take too many of your comfort zone in this talk. I mean, this is going to be a mathematical talk. When Arthur invited me to participate in this conference, this was one of these experiences when I said, this is probably sent to the wrong person. And I actually replied to the invitation saying, I didn't do anything quantum in my life. You probably wanted to send it to somebody else. And then we had a discussion. And my conclusion from this discussion is that maybe due to some recent interest in hypercontractive inequalities in the quantum world, that would be a good topic for discussion. And that's what I'm going to talk about. But given the audience, I'm also happy for you to give me feedback. And if you want me to talk more about the applications and less about the basic mathematics, feel free to ask questions during the talk. Okay, so sorry, there's going to be I think there's no pictures, there are many equations and probably there's no pictures in my slides, right? So it's very different from the previous talk, but I want to explain to you the basic mathematical concept here and, just to give you a flavor of this area. And there is some notation here, so I'll try to pass it from you. But the basic picture that we have here is sort of the simplest statistical physics dynamic model, which is just a random walk on the discrete hypercube, right? So this is the discrete hypercube in 3 dimensions, and I have a random walk on this cube, right? So I go to one of my neighbors and I do it at rate 1. So at rate 1 means that if I run from in n dimension, I'm going to go about in time t, I'm going to go to distance of order n. So we are interested in this random walk. We are starting maybe at a random point, and then we take this walk and we get a correlated point, and we want to understand the correlation between the starting point and the end points. And this is what's called in mathematical language, this is the Markov operator for this random walk. And in mathematics, we all often like to work with, we understand how Markov operators act on functions. So what's written here is, that's the usual language when we study the operated version of the Markov chain. We want to know that we started from the point X, we took a random walk, we got to some random point Y. And what we want to know is, given that I started off at X, what's the expected value of where I landed? Okay, so that's sort of the basic question here. And obviously, because of this random walks around, you get some smoothing. So you have some diffusion. And there's a long story here, and I want to concentrate maybe on one caveat of this long story. But before I do that, let me tell you sort of the classical theory that goes to Bonamy, Beckner, Gauss, 1960s, is that we have this amazing fact about this operator. It does something that we rarely see in your basic analysis classes. What we do here is we compare the Q norm and the P norm of 2 functions. So usually, we know that Q norm of a function is bigger or equal than the P norm of a function. What this Markov operator does, what this diffusion does, since you diffuse, actually the P norm, the higher norm of this average function of this TTF, where you, instead of looking at the point, you average over all the places you can go to in T times, is smaller than the Q norm of F, where P is actually bigger than Q, as long as you run for long enough time, right? So the long enough time is given by this expression over here, and that was proven in the 1960s or 70s. So this is a super. Nelson. I forgot Nelson. Yes. So no, Nelson, and of course, there's the history here is complicated, and thank you, Arthur. We also have to mention Nelson. It was first proven in the Gaussian case, but I'm going to talk mostly about discrete cases, which imply the Gaussian result. And this is a very strong analytical tool, and I'm going to explain to you why before maybe I talk about the more exotic variant of this. Okay, so this is used a lot. I'm just, this sounds like very, maybe you say, why is this analyst telling us about this analytic inequalities? Well, first of all, I'm not an analyst. I like these inequalities because they're useful, and it's used a lot. Somehow this inequality is very powerful, so it's used a lot in the theory of phase transitions, in random graph, in percolations, in codes. I mean, this is Kahn-Kalai lineal, Friedgut, the recent progress by Pivier's Urbank and their student on achieving capacity for erasure codes. So this is a very strong tool in phase transition. It's used a lot in percolation. Benjamin Nikolai Schramm and Steif and Schramm and others. It's used a lot in understanding voting theory. And I won't really try to explain to you how it's used in all of these places, but I just want to give you a little bit more of the analytic flavor of why this is useful. Just that if you've never seen it before, you get some intuition why this is good. So I'll give you two point of views or two of the very basic ways where this is used. So remember, we have this X and Y. So I'll just draw the same picture again, right? So we had a random walk on the discrete cube, and I started at the point X, and I walked and walked and walked, and arrived to some point Y. And one thing I can try to study is the correlation between f of X and g of Y. Okay, so I can ask what's the expected value of f of X and g and Y, and if you remember your basic analysis class, there's an inequality that's called Cauchy-Schwarz, and Cauchy-Schwarz will tell you this is less than f norm 2, this is 2, g norm 2. But somehow the fact that x is not y, x is just correlated with y, give you a much stronger inequality. So instead of getting the 2 norm here and here, you get lower norms. And in particular, the condition is you can do it as long as the norms satisfy that p minus 1 times q minus 1 is bigger than e to the minus 2, right? So in analysis, we'll use a lot the Cauchy-Schwarz inequality. This is a stronger inequality. If instead x and x, you get x and y, where y is correlated, you get a stronger inequality. And of course, this buys you a lot in cases where you need something stronger than the Cauchy-Schwarz. Maybe another intuition that's good for discard, so you all know the Fourier uncertainty principle, maybe an Rn, or respect to the Gaussian measure. But this, when you have hypercontractivity, you have Fourier uncertainty principle with respect to other groups. So I'll show you in this group, right? So maybe one particular way where this is used a lot is we use it for S, right? So the picture that I have in mind, it's not Rn, but I'm going to draw the picture like this is Rn. This is my space, and I'm looking at a tiny, tiny set that has a very, very small support, right? So the Fourier uncertainty principle should tell me that if I have a set with small support, something interesting is happening in the Fourier spectrum. All the Fourier spectrum, much of the Fourier spectrum should lie on big or high amplitudes, and this you can derive very quickly from this hypercontractive inequality. I mean, you can easily see that the L2 norm, the L2 norm of the L2 norm of the indicator of the set is exactly the probability of the set. And when you apply this hypercontractive inequality, you get this inequality. You get that if you apply this averaging operator on this indicator, you get something when P of A is small, it's much smaller. Right, so now instead of having the probability of the set, we have a power of the probability of the set that's bigger than 1. Because it's bigger than 1, we get a tiny number, and it says that the L2 norm of the Fourier of this is very small. So I didn't tell you what's the relationship between this operator and the Fourier norm, the Fourier spectrum. But this operator, high amplitudes, it dampens a lot, and low amplitudes, it sort of keeps the same. So this is telling you in words. It's telling you. I'll just write it in words. Most Fourier. So I didn't even define what's the Fourier spectrum, but most Fourier spectrum is on a high amplitude. Okay, so that's the sort of two reasons why we look at this. Okay, so again, I'm not going to prove anything, but I just want to give you the lay of the area before I go to more exotic version, which I think I'm going to spend most of the talk on. So hypercontractive inequalities are sensitive in the sense that they depend a lot on the space that you're looking at. So they're sensitive, and okay, they're somewhat hard to prove. And I'll just give you some example to show in what sense they're sensitive. So before I looked at my random walk, I can think about it whenever I take a move, I toss a coin and I decide according to this coin if I, this coordinate that I'm changing is going to be 0 or 1. Now you can do the same thing where the coin has probability alpha. So with probability alpha, I'm going to get 1. With probability 1 minus alpha, I'm going to get 0. So it's a different random walk, right? It's not uniform everywhere. It sort of flies on vectors of weight around n alpha. But you can still study this random walk. And if you study this random walk, and you can ask, how hypercontractive is it? So you get something similar to what we've seen before. So I won't tell you, sorry, there's t here, if and only, oops, t is bigger than this quantity. The key aspect of this quantity that I want to talk about is this log 1 over alpha. So if my coin is very, very biased, in order to get the same kind of dampening of the spectrum or the same kind of contraction that I had before, I have to wait much, much longer. And this is actually a technical obstacle in proving many, many results in this area when you talk about probabilities that are biased. And maybe I'll get to that later. Similarly, or relatedly, you can prove sometimes hypercontractivity of Glauber dynamic or the heat bath dynamic for many statistical physics models. So there's a long line of work in stat physics. Okay, I'm not really going to mention talk about that. And then there's quantum versions, which I'm also not going to talk about, right? So depending on the operator, it has to be the right operator. If it's the right operator, maybe you can prove it, maybe you cannot prove it. It depends on your situation. Okay, so that's the sort of the story of hypercontractivity that I wanted to tell you. Okay, so what I wanted to tell you is something very peculiar. So even the mathematicians in the room, I expect to be a little confused by all of the inequalities that I'm going to present now. So, the non-mathematicians, you should feel very comfortable being confused, okay? Because everything that I'm going to say now is going to sound very strange. And it sounded very strange to me the first time that I've seen it. So in the 80s, two Swedish mathematicians, Borel and Janssen together in a paper said, well, actually you can do something similar in the same setting for positive functions. Okay, so I'm writing to R plus, the functions only take positive values, but I'm going to do things a little different. My norm are going to be less than 1. Okay, any objections from anybody? It's not a norm, very good. So let's ignore that point. It's not a norm. My norms are going to be less than 1. And moreover, the inequality is going to go in the opposite direction. After I average, the Q norm is going to be bigger than the P norm. Okay, so with the first time I've seen it, a few things happened simultaneously. A, I didn't believe it. B, I got a headache. And C, I had to check the proof, right? Because how can something like this be true? Everything is very wrong. So it's not a norm, but I'll just say that you can still define it, right? So f, you just define fp to the p is the integral of f to the p, according to whatever measure you're looking at, right? And and p can be any number. It can even be a negative number, right? So p can be any number. I can take p equal to 1/3 or p be equal to -10. It's a positive function. I can do it for any p that I want, okay? So that's the result that they prove, and the proof is correct. And I even have the proofs in the slide, but I probably am not going to talk about it. Okay, so also when they noticed it, they were like, they didn't really see a reason why would this be interesting. They were like, just, okay, notice that it also works in this dual sense. And it's not really dual in the case where P and Q is less than 1. Okay, so I want to tell you a little bit about it. First of all, I want to tell you if it makes sense, and then I'm going to tell you why it might be interesting or what's the application of this inequality, and a little bit about more advanced theory of this inequality. Okay, so again, just for the mathematically minded people among you, let me just try to say why it makes sense. So the first thing is that when P is less than 1, the triangle inequality goes the other way. So instead of f plus g norm being less than f norm plus g norm, it goes the other way. If f and g are positive, f plus g norm is bigger than f norm plus g norm, okay? And this translates more generally. If you average, if t is a Markov operator, you get this inequality here, tfp is greater than fp. This is not the inequality that I've shown you before, because here it's the easy case where the norms are the same. P and p here are the same. So for the same norm, if you average, it's getting bigger. Similarly, if you look at Cauchy-Schwarz or Helder inequality, so there isn't really Cauchy-Schwarz, but Helder inequality also goes in the other direction. So if you look at the expected value of fg or the L2 norm of fg, because these are positive functions, it's bigger or equal than fp norm times gp prime norm, where p prime is the dual norm. So it again goes in the opposite direction. And when you look at it this way, you say, well, maybe, this is not such a surprising inequality. When the norms are less than 1, all of the inequalities are reversed. So everything should work out, right? So it sounds like magic, but in fact, it does work. And, you get this inequality that Borel proved. Okay. Okay, so let me try to tell you a little bit. So I actually have the full proof here. I want to talk a little bit about why is it true. So, and then the actual proof I want to, the actual proof is, is some computation, but I'll tell you the softer part of the proof. So the softer part of the proofs are exactly like the classical hypercontractive inequalities. There's a few things that work here together in your benefit. So first of all, you can tensor. So tensor means it's enough to prove it in one dimension. And in the usual case, you can tensor because of Minkowski's inequality. You can check that it works out. Here you have the reverse Minkowski inequality. So it's enough to prove it in one dimension. There's duality, like there's duality in the norms that are bigger than 2. There's duality for norms that are less than 2. So it turns out that at least you don't have to worry about 2 exotic norms. You don't have to worry about norms where P is negative, right? P is negative is really hard to wrap your mind around. So it's enough to look at P and Q between 0 and 1. And duality and continuity do the rest for you. And then you just have a function. So remember, we are just looking at the discrete cube. We are in one dimension. So our situation is the following. Our function now is a function. So in one dimension, we have a function just from plus minus 1, 2 values. It's a function that takes 2 values to r plus, to the positive numbers. Okay, so these functions, obviously, you can write as a linear function. And, because it's positive, a is between -1 and 1. And then you do some Taylor expansion. And, if you go to a Russian school or you're Borel and Jensen, you do it in 5 minutes. If you're me, you'll do it in 2 hours. You'll see that this inequality is correct. Okay. So that's how Borel proved it. And I mean, you don't have to look at this slide, but this is the full proof, right? So, this is the Taylor expansion. You have to work with this binomial coefficients. You have to do it, and then you get what you get. Okay. Okay, so I showed you hypercontractive inequalities. I was trying to argue why they are important. I showed you the reverse ones, and now I want to tell you a little bit why they're interesting. So I'll tell you a couple of stories of why they're interesting, and then maybe a little bit more of the theory or the more advanced directions in this area. So we started looking at it around 2005 in a joint work with O'Donnell, Regev, Steif, and Sudakov. And the setting is exactly the setting that we had before. So I mean, the x and y's are exactly the x and y that we had before. X is chosen uniformly at random. Y is after I perform this random walk. And now I want to understand the following picture. Again, I'm going to draw my discrete cube here. I'm going to draw it maybe like this. And now what I'm interested in is I'm interested to know what's the chance that x lies in this set here and y lies in this set here. Okay, so I start my points. X is started uniformly at random, then y is a correlated point. I want to find a lower bound actually on the chance that x is in A and y is in B. So for those of you who are from computer science or combinatorics background, there's the expander mixing lemma that tell you something in this direction. Expander mixing lemma depends on the spectral gaps. It only works for large sets. We wanted something that works for small sets, and it turns out that this two-function version of this hypercontractive inequality gives you something like that. So it tells you that if the probability of A is at least epsilon, the measure of A is at least epsilon, the measure of B is at least epsilon, that the measure of that X is in A and Y is in B is at least some power of epsilon independent of the dimension. Right, so that's the kind of inequality that you get, and it's very useful, and it's almost tight up to the logarithmic factors in epsilon. When epsilon is small, it's almost tight. Okay, so that's one version. Okay, so that's nice, right? It's something that you often don't have, right? It's sort of, if you want to think about it in terms of, I don't really know anything about quantum theory, but it's in quantum theory, if you have a result like that, it's probably bad because it means that different parts of the system interact a lot, right? You can go from everywhere, you can get to everywhere with reasonable probability, right? So if you can prove an inequality like that, you have to be somewhat careful about, entanglement maybe and so on and so forth. Maybe I'll spend 1-2 minutes on what really started us on this problem. And this, I think, is a really cool problem that's really not, has no practical implications, but this is what started Ryan and I many years ago on this problem. So we were bored before the days of COVID, and we wanted to ask, could many players play poker online together? Okay, so of course, there are many papers on it, but what we actually have is we have the following situation. So here's the center of the star. In the center of the star, here, there's a sequence that we call the cosmic background. This is x1, x2, x3, x4. They are IID plus minus 1. Meaning these are just random coin tosses. We want to use these random coin tosses to toss the same coin together. So how are we going to do it? Here's player number 1. Player number 1 gets y1, y2, y3, and so on and so forth. Player number 2 gets z1, z2, z3, z4, and so on and so forth. And what is the relationship between x and y? X and y is, the relationship between them is exactly, I started from x. So maybe I'll draw the picture here. So I started from x once, I took a random walk on my cube, I got y. I started from x another time, I took a random walk on my cube, I got z. I started from x, I took another random walk, I got w, right? So there's a little bit of noise. We are not all receiving exactly the same sequence. Still, we all want to toss the same coin. We're good? Okay, what's the best strategy to toss the same coin? So I got 1,000,000 bits, Arthur got 1,000,000 bits, Yuri got 1,000,000 bits, right? You know, many of us got 1,000,000 bits. We all want to toss the same coin. It has to be an unbiased coin, right? We cannot say, oh, let's just all decide we all do one. Then obviously we'll agree, but that's not fair, right? It has to be a 50-50 coin, and we want to maximize the probability that we will all output the same answer. Any suggestions? So one option is for all of us to say, we'll just take bit number 1. Okay, so let's say, so one option is to say, let's take x, let's take y1, z1, and so on and so forth. Then what's the probability they will all agree? This is something like it was in Yuri talk. It's essentially, it's essentially 1/2 times 1 minus, 1 minus e to the minus t to the number of players, plus 1/2, something like that. So it's essentially, sorry, no, it's just that. So it goes down exponentially. I think I have a typo here, but it goes exponentially in the number of players. For everybody to agree, you know, the first player has to agree, that's a constant probability. The second player has to agree, that's a constant probability. All of this probability is independent, so it's exponentially in the number of players. In previous work, we actually showed something interesting, that if instead of taking y and z and so on and so forth, what they do is they take the majority of x, sorry, the majority of y, the majority of z, the majority of w, then the probability that all players agree decays like a power of the number of players, depending on a power that depends on t. Okay, so it doesn't decay exponentially. Even though you have many players, the probability that they all agree is actually decaying just polynomially. And then in the previous work, we asked, well, maybe it doesn't decay at all. We found an example where it decays polynomially, but maybe it doesn't decay at all. Maybe no matter how many players we have, we can agree with probability at least 1/10. And we couldn't prove it. We couldn't find any function that would do it. And we couldn't prove that you cannot, and we were stuck until with Oded and Benny, we found this hyper-contractive tool. It's not easy to show, and this we knew before, that you can express this agreement probability in terms of this noise operator and actually high norms. So you can express this in terms of this TTF to the k, norm k to the k, and TT1 minus f to the norm k to the k. So that's an analytic expression. And I won't tell you how, but it's pretty easy from this reverse hyper-contractivity to prove that each of this expression here, and this expression here is lower than some power of k. Okay, so what does this mean in words? It means that if you have large number of players, this protocol of everybody taking the majority of their bits is optimal again up to logarithmic terms. And the agreement probability in this protocol is not exponential in the number of players, it's polynomial in the number of players. Okay? So that was the story for us, right? So that was one of the main reasons we were interested in this. Okay, so that was one story. I can tell you many other stories of uses of this inequality. I mean, it's used in what's called social choice theory. I mean, this is, how many of you have heard of our theorem? Okay, so there's our theorem, there's quantitative versions of our theorem. How many of you have heard of Gibert-Satterwhite theorem? No. So you should look Gibert-Satterwhite theorem, what it is, because that's the more depressing theorem. Our theorem is slightly depressing, because it tells you that there is no rational way to rank candidates. The G-bar-Satterwise theorem is more about a single winner. And it tells you that in the case of a single winner, there's no method with a single winner where you have 3 or more alternatives where nobody would want to manipulate. Okay, manipulate means voting dishonestly. And this actually created a huge crisis in this area. People were like, this is very depressed. Let's not study this area ever again. Okay, essentially, that's what happened after this result of G-bar-Satterwise, after a few years after. But the mathematicians, we were interested in quantitative versions of that. And in quantitative version of that, it turned out that this reverse hypercontractivity is very important. Okay, so what should I tell you next? How much time do I have? 5 minutes. Okay, good. So I'll skip this. So what was the what are maybe a couple of interesting aspects about hypercontractivities versus reverse hypercontraction? So one interesting aspect, so maybe I'll put the slide again. So, these are the, I show it in, I make the comparison between the Bonamy-Beckner inequality written over here and the Borel inequality written over here. This is for the same space, and they look exactly the same. I just flipped all the signs, right? And then if you see two things where you flip all the signs, for some time we held the conjecture that these two inequalities are equivalent, not just in this space, in all spaces they're equivalent. And surprisingly, it turned out in this work with Oleshkevich and Chen that it's not equivalent. And in fact, it's much easier to have reverse hypercontractivity than to have hypercontractivity. So the reverse hypercontractivities, I mean, there's a lot of words here, but the reverse hypercontractive inequalities are easier to prove. They follow automatically from the hypercontractive inequalities. And there are many cases where you have reverse hypercontractivity without having hypercontractivity. Okay, so it's a different theory. It sounds like maybe at the beginning, it sounds like it's the same theory, it's a different theory, and that was interesting for us. And these are the bunch of applications, but maybe just for the expert, I'll sort of think about interesting connections and direction for this. And I'll do that in the last 5 minutes. I just want to give hints of, so this, for me, this is all work that was done about 10 years ago, and I want to tell you about some more recent connections, especially since there's some quantum follow-up to this reverse hypercontractivity that some of you might find interesting. So the same Borel in 85, in the Gaussian case, which we didn't talk about at all, proved tight bounds. Tight bounds mean the exact number, no logarithmic loss, nothing. It's a geometric bound for the probability that X is in A, Y is in B. I mean, so that bound is met by some set A and B. And in the Gaussian case, there are bounds for multiple sets. I don't know how many of you have seen the Berskamp-Lieb inequality or reverse Berskamp-Lieb inequality. They are of the same form as the hypercontractive inequality, but they include multiple sets. In the discrete spaces that I was talking about before, like the discrete cube or bias cube and so on and so forth, somehow there's an interesting story partitioned into two parts. One of them are what I call product with full support. And in this full support case, there's two interesting stories. Again, I'll say it very quickly. You can prove general bounds of this form via the theory of hypercontraction or reverse hypercontraction. And maybe more interestingly, you can prove that the Gaussian picture is the correct, gives you the correct bound for resilient functions. So what are resilient functions? Resilient functions are functions where all of the Fourier coefficients are small. So if it turns out that if all of the Fourier coefficients are small, actually you can carry out everything that you know from the Gaussian theory, including the Berskamp-Lieb inequality and the geometric inequality to discrete spaces. And just to make it more complicated for all of you, this is a complicated picture. There's the case of discrete spaces without full support. And this actually includes all of additive combinatorics on finite fields. And in additive combinatorics on finite fields, all of these techniques break down, right? So all of these techniques are irrelevant. And instead of these techniques, you actually have to use some other techniques, including use bounds using the Gauss norms and so on and so forth, that are of different flavor. And somehow one very interesting research direction, which I'm interested in the last 5 to 10 years, is sort of bridging the gap between this, more analytic theory and more symmetric-based theory or linear algebraic-based theory of the Gauss norm. So that's one picture. And maybe another picture that I find very exciting is what's called global hypercontraction. So like we said before, if you look at the bias cube where you toss your coin, it's very biased. then you don't have hypercontractivity, it's just phase, it's easy just to show that it phase, but still there was a redemption, recent work by Kivash, Lifkitz, Long and Mincer showed that you have hypercontractivity for global functions, and global functions are functions that are not too local. They have a technical definition for what does it mean to be a global function. And I think this again might be something that might be of interest to generalize into the in the quantum case and also in the reverse hypercontractive sense. Okay, so sorry for dumping all this on all this math on you, and I'm happy to take questions.
I think during Tuesday, Ulrich's talk, he mentioned your, talk actually. So if that's some specific application, he used those kind of.
No, this is unrelated. I mean, so yeah, so I do a bunch of things. That's one of the things I do. It's to the best of the techniques that we use there are not of this nature, right? So they're different.
So it's not used in any approval.
Yeah.
Okay.
Yep.
Hi, Professor. I'm Li Yuan, and I just confused that do we have any quantum version of this random work, and can that be used into those quantum random work?
Yes, but you should ask people who understand about quantum things, right? So so yes, so this there is the quantum random walk. This is something that's studied a lot. The mixing time of the quantum random walks is studied extensively, and hypercontractivity and reverse hypercontractives are used for analysis of the quantum random walk. Yes.
Okay, thank you.
Oh, this is Zhao Yang. I just wonder, so for your random walk, it's the site, it takes value 0 and 1. How about the global dynamics, like in Potts model, the site can take value from 0 to p?
Right.
So do you also have those hypercontractivity?
Right. So I mentioned in one line in the slide that for stat physics model, in high enough temperature, I mean, it's not necessarily just below the phase transition, depending on the model, but in high enough temperature, starting from work of Foley and Strook and Zygarlinsky, and so on and so forth, they establish hypercontractivity. And our general theory says that whenever you have hypercontractivity, you also have reverse hypercontractivity.
Oh.
So for high enough temperature, you get it. You get it. Yeah.
Thank you.
Oh, this is Kaipeng. So my question is, could you give example how is Gauss norm used in hypercontractivity?
No, so Gauss norm is an alternative to hyperconductivity, right? So what happens is that if your space doesn't have full support, like if you look at the space of all arithmetic progressions over some finite field, this doesn't have a full support. There isn't a positive probability for every sequence of possible values in f to the n or f to the k. So there, in order to prove bounds about the probability that say, x1 is in A, x2 is in B, x3 is in C, you cannot use these techniques. They do not apply, right? The reverse, we don't know how to apply them. So the Gauss norm is an alternative to that, but the unfortunate effect of the Gauss norm or version of the Gauss norm is that they usually require some symmetry of the space, right? So, and so they work when they work, they give the bound that they give, but if you are looking at a situation that may be less symmetric and doesn't have full support, so the analytic technique fails because they require full support, right now at least. The Gauss norm techniques fail because they don't have enough symmetry, and we really don't know how to prove things in this area, except, we have some partial result in some cases, but that's sort of the interesting case, right? So it's either one or the other, right? So, yeah.
Thank you. Any other questions? If not, let's thank Elchanan. Thank you.